Factors, Class Life Sciences. Part 1. Influence of the variation in concentration of reactants. At the end of this session, students should be able to define kinetic factors, identify the effect of variation in concentration of reactants on the rate of the reaction. Introduction. Have you ever wondered why you keep food in the fridge and why food like meat spoil quickly outside the fridge? Is it possible to accelerate or slow down a chemical reaction? Factors such as concentration of reactants, temperature, surface area of contact between reactants, catalyst, are among factors that may affect the rate of a chemical reaction. These factors are called kinetic factors. Then kinetic factors are any factors that may affect the rate of the reaction by increasing it or decreasing it. 1. Influence of concentration of reactants. Study of the reaction between H2O2 and I- in acidic medium at constant temperature, starting with different initial concentration of I-. Then we will study the effect of the variation in concentration of one reactant, I-. Procedure. Consider the following solutions. S1 potassium iodide solution K plus I- of concentration C1 equals 0.145 mol per liter. Solution 2 sulfuric acid solution H2SO4 of concentration C2 equals 1 mol per liter. And solution S3 hydrogen peroxide solution H2O2 of concentration C3 equals 0.045 mol per liter. Use 3 empty beakers. Add the colorless potassium iodide solution K plus I- of concentration C1 equals 0.15 mol per liter. First 10 ml in beaker A and 20 ml in beaker B and 40 ml in beaker C. Then add the colorless sulfuric acid solution H2SO4 of concentration C2 equal 1 mol per liter, 10 ml in beaker A, then 10 ml in beaker B, and 10 ml in beaker C. Add distilled water to make the volume in each beaker equal to 90 milliliter. In beaker A we put 10 milliliter of Ki and 10 milliliter of H2S for 20 milliliter. We need 70 milliliter of distilled water. And in beaker 2 we add 20 milliliter Ki and 10 milliliter H2SO4, then 30 milliliter, we need 60 milliliter of distilled water. In beaker C we have 40 milliliter Ki and 10 milliliter H2SO4, 50 milliliter, we need 40 milliliter of distilled water in beaker C. Now, at this moment, no reaction taking place between I- and H+. Add to the 3 beakers at the same time 10 milliliter of the colorless hydrogen peroxide solution H2O2 of concentration C3 equals 0.045 mol per liter. At the same time, we pour the 10 milliliter of H2O2 in each beaker. Now, each beaker contains 100 milliliter of reactants. At this moment, the reaction starts. At the beginning, the solution before the starting of the reaction in the 3 beakers is colorless. Observations. The color in each beaker changes progressively from colorless to yellow, then to red-brown due to the slow formation of iodine I2. As we have seen in the two pictures, the color changes from yellow to red-brown. For the same interval of time, the darkness of the color in beaker A is less than that in beaker B, less than that in beaker C. At the end of the reaction, the three beakers have the same color. The concentration of I2 formed at the end of the reaction is the same in the three beakers, and we will see why in the part interpretation. This video shows this experiment. Reaction between iodide ion and another experiment, but same observation, and S2O8 2- ions, iodide ions and peroxide disulfate ions. The net equation is 2I- plus S2O8 2- give I2 plus S2SO4 2-. The following table resumes the conditions of the experiment. We have two beakers. In beaker 1, we put 20 milliliter of I- Ki solution of concentration 0.1 mole per liter and 20 milliliter of S2O8 2- solution of concentration 0.05 mole per liter. In beaker 2, we put 20 milliliter of Ki solution but of concentration, initial concentration 0.01 mole per liter, less than the initial concentration in beaker 1. For the Na2S2O8 solution, the same volume and same initial concentration. Then between beaker 1 and beaker 2, we changed only the initial concentration of I-. The initial concentration of I- in beaker 1 is bigger than that in beaker 2. What is the effect of this change or decrease in the rate of the reaction? On the rate of the reaction, we will see. We have 20 milliliter in each beaker of K2S2O8 solution. Now, in this graduate cylinder, we have 20 milliliter of Ki 0.1 mole per liter, and the second graduate cylinder, we have 20 milliliter of Ki 0.01 mole per liter. Now, at the same time, we will add the Ki solution in the two beakers. We observe the appearance of yellow color in beaker 1. And the color in beaker 1 is darker than that in beaker 2. Beaker 2, now we will observe the appearance of light yellow color, while in beaker 1 it becomes dark or red-brown solution color. That means the concentration of I2 or the I2 formed in beaker 1 is the amount of I2 formed in beaker 1 is higher than that in beaker 2 for the same interval of time. Okay, we will interpret this observation in next part. Interpretation. Net equation of the reaction. H2O2 with 2I- react with 2I- and 2H plus to give I2 and 2H2O. This is the net equation of the reaction. Now the initial concentration of each reactant. In order to calculate the initial concentration of each reactant in the reaction mixture, we should calculate the initial number of moles, then we divide it by the total volume of the mixture. For I-, in beaker A, initial number of moles of I- equal initial number of moles of Ki equals C1 times V1 equals 0.15 C1. V1 10 milliliter, that means 0.01 liter, equals 0.0025 mole. Initial concentration of I- equal N0 I- over V total, 0.0025 over 0.1. Then the initial concentration of I- in beaker 1 equals 0.025 25 mole per liter. The same in beaker B, N0I minus equals C1 V1 equals 0.05 mole, divided by total volume, the initial concentration of I minus in beaker B equals 0.05 mole per liter. Also for the same for beaker C, N0I minus equals C1 V1 equal 0.01, V1 equal 40 milliliters, 0.04 liter. Initial concentration, we divide initial number of mole by B total equals 0.1 mole per liter. For H plus, in the three beakers, N0 initial number of mole of H plus equal 2 N0H2SO4 equal 2 times C2V2 equal 2 times 1 C2V1 V2 equal 10, 0.01 liter equal 0.02 mole divided by total volume, which is 100 milliliters, that means 0.1 liter, then initial concentration of H plus in the three beakers 0.2 mole per liter. For H2O2 in the three beakers, N0H2O2 equal C3 times V3 equals 0.045 times 10 milliliters, 0.01 liter equals 0.00045 mole divided by total volume. We obtain the initial concentration of H2O2 0.045 mole per liter. This table summarizes the initial concentration for each reactant in the three beakers. For I minus 0.025, in beaker B 0.05, in beaker C 0.1. Then the initial concentration of I minus increases starting from beaker A to beaker C. For H plus, initial concentration is the same in the three beakers 0.2. And for H2O2, initial concentration is the same in the three beakers. Then the only difference between the three experiments in the three beakers is the initial concentration of I minus. What is the effect of this variation in initial concentration of I minus on the rate of the reaction? Now, limiting reactant. In order to determine the limiting reactant, we should calculate the ratio for each reactant from the initial number of moles calculated in part 1. In beaker A, for I minus ratio of I minus equal N0 I minus over H stoichiometry 2 equals 0.00125. For H plus, ratio of H plus equal N0 H plus over 2 equals 0.02 over 2 equals 0.01. For H2O2, ratio equal N0 over 1 equals 0.00045. By comparing the three ratios, we found that ratio of H2O2 less than ratio of I minus less than ratio of H plus. Then H2O2 is the limiting reactant while H plus and I minus are in excess. The same for beakers B and C. In the three beakers, H2O2 is the limiting reactant. Now, concentration of I2 at the end of the reaction. In order to determine the concentration of I2 or any product at the end of the reaction, we should determine the number of moles of this product at the end of the reaction using the limiting reactant, always using the limiting reactant. Then we divide this number of moles by the total volume. According to the stoichiometry of the reaction, in the three beakers, we have number of mole of I2 at end of the reaction over 1 equal initial number of mole of H2O2 over 1 since the reaction is complete. Then number of mole I2 at infinity equal 0.00045 mole divided by the total volume. We obtain the concentration of I2 at end of the reaction at infinity equals 0.0045 mole per liter. The three beakers then have the same concentration of I2 at infinity at end of the reaction, so that the final color in the three beakers is the same. At end of the reaction, we have the same color in the three beakers. Relation between the intensity of the color and the concentration of I2. The color of iodine solution changes from yellow to red-brown according to the concentration of I2. When the concentration of I2 increases, the color of the solution becomes darker. For the same interval of time, the intensity of color in beaker A less than that in beaker B less than that in beaker C, so that the concentration of I2 formed at the same instant in beaker A less than that in beaker B less than that in beaker C. Effect of the variation in the initial concentration of I- on the rate of the reaction. For the same interval of time, delta T, we found that concentration of I2 formed in beaker A less than that in beaker B, less than that in beaker C. And since the average rate of formation of I2 equals variation in concentration of I2 over variation of time, same delta T, we have concentration in A less than that in B less than that in C, then rate of formation of I2 in beaker A less than that in beaker B less than that in beaker C, not at instant T because it is average rate, the same instantaneous rate at instant T. Okay, and since the initial concentration of I- in beaker A, why the rate of formation of I2 in A less than that in B less than that of C? Because the initial concentration of I- in beaker A is less than that in beaker B, less than that in beaker C, while initial concentration of H plus and H2O2 remain constant, the same initially. Therefore, we can conclude that when the initial concentration of I- increases, the rate of formation of I2 increases and vice versa. Then the initial concentration of I- is the kinetic factor. This factor has increased the rate of the reaction from beaker A to beaker C. General conclusion: when the concentration of reactants increases, the rate of the reaction increases, and vice versa. That means when the concentration of reactants decreases, the rate of the reaction decreases. Therefore, the concentration of reactants is a kinetic factor. Remarks, very important. If we repeat the same experiment many times, the same reaction many times, by changing only the initial concentration of the same reactant, then the kinetic factor is initial concentration of this reactant. As we have seen in the experiment between I- and H2O2 in acidic medium, we have changed only the initial concentration of I-, then the kinetic factor in this case was the initial concentration of I-. In chapter 1, we have studied that the rate of the reaction decreases with time. Why? Because during a chemical reaction, the rate of the reaction decreases with time because the concentration of reactants, all reactants, if they have concentration, all reactants that have concentration, their concentration decreases with time. Since the concentration decreases with time, then the rate of the reaction decreases with time till the end of the reaction where the concentration of limiting reactant becomes zero, then the rate of the reaction becomes null. The reaction is ended. At the end of the reaction, the concentration of the limiting reactant is zero, so that the rate of the reaction becomes equal to zero. Therefore, the kinetic factor in this case is the concentration of reactants, all reactants. But we have an exception. For example, in the reaction between metals, for example, Zn and H3O plus acid, that gives Zn2 plus H2 plus 2H2O. Zn is solid. Solids all solids that are not dissolved in water have no concentration, because by definition the concentration is the amount of solute dissolved in water, in 1 liter of water, distilled water, or solvent. Since solid does or do not dissolve in water, then solids have no concentration. In this reaction, the only reactant that has concentration is H3O+. In this case, the rate of the reaction decreases because the concentration of H3O+ decreases, so that the kinetic factor in this case is the concentration of H3O+, not concentration of reactants, because Zn has no concentration. In case of a decomposition reaction, only one reactant, the reaction that has only one reactant, is called decomposition reaction or dissociation reaction. For example, in general, A gives B and C, but A should not be solid, could be solution, ionic compound dissolved in water, or liquid. That means a reactant that has concentration. Solid has no concentration. The rate of this reaction decreases with time because the concentration of reactant A decreases with time. Then the kinetic factor is the concentration of A. For example, the reaction of decomposition of H2O2 that gives H2O and half O2. In this case, the rate of this reaction decreases with time because the concentration of H2O2 decreases with time, so that the kinetic factor in this case is the concentration of H2O2. If we repeat this experiment many times by changing only the initial concentration of reactant A, then the kinetic factor is this. In this case, is the initial concentration of A. That means if we repeat the decomposition reaction of H2O2 many times by changing the initial concentration of H2O2, the kinetic factor in this case is the initial concentration of H2O2. Application: we realize the experiment between Mg and an excess of hydrochloric acid H2O plus Cl-. The net equation of the reaction is Mg plus 2H2O plus give Mg2 plus 2H2O plus H2. We repeat the experiment with one modification. The solution S1 of hydrochloric acid, that means of H2O plus, is replaced by solution S2 of concentration C2, where C2 bigger than C1. That means initial concentration of H2O plus in experiment 2 bigger than initial concentration of H3O plus in experiment 1. The end of the reaction is reached faster. The number of moles of hydrogen gas produced at the end of the reaction increases. These are two propositions. The question is, indicate if each proposition is correct, justify. If it is correct, why? If it is not correct, also why. We have in the given the hydrochloric acid, that means H2O plus, is in excess. That means Mg is the limiting reactant. The initial concentration of H2O plus increases, then the rate of the reaction should increase because the initial concentration of H2O plus is a kinetic factor. Then when the rate increases, the time needed to the end of the reaction decreases. That means the reaction is reached faster, then the proposition is true. The number of moles of hydrogen gas, that means the product, produced at the end of the reaction increases. We know that to calculate the number of moles of H2 at the end of the reaction or any product, we use the limiting reactant Mg. According to stoichiometry, initial number of mole of Mg equal number of mole of HU at end of the reaction. But since the initial number of mole of Mg remains the same because the only change is the increase in the initial concentration of H2O+, we did not change the initial quantity, the initial mass or number of mole of Mg. And since the reaction is complete, then we should obtain the same number of mole of H2 at the end of the reaction. But this number of mole is obtained faster in the experiment 2. Then proposition 2 is false. The answer to proposition 1, the end of the reaction is reached faster since the initial concentration of H2O+ is the kinetic factor. When it increases, the rate of the reaction increases. Then the time to reach the end of the reaction decreases. Proposition 2 false, since the number of moles of the limiting reactant, which is Mg, remains the same, and the reaction is complete, then the number of moles of hydrogen gas produced at the end of the reaction remains the same. Application 2. Consider the reaction C6H5N2Cl gives C6H5Cl plus N2. This is a decomposition or dissociation reaction. The rate of disappearance of benzene diazonium chloride C6H5N2Cl at T1 equal 150 seconds is equal to 8.7 times 10 minus 5 mole per liter per second. And at T2 equal 465 seconds, and time increases, is equal to 610 power minus 5 mole per liter. When time increases from 150 seconds to 465 seconds, the rate decreases from 8.7 10 minus 5 to 610 minus 5. The question is, specify the kinetic factor responsible for the change in the rate between T1 and T2. We know that during the reaction, the rate decreases with time because the concentration of the reactant C6H5N2Cl decreases with time. So that the kinetic factor is the concentration of C6H5N2Cl. Solution. The rate of disappearance of C6H5N2Cl decreases with time due to the decrease of the concentration of C6H5N2Cl with time. Then the kinetic factor responsible for the change in rate is the concentration of C6H5N2Cl. (1.4) Effect of the variation in concentration on the shape of the curve. Sorry. 141. Effect of the increase in concentration of a reactant. If we repeat the same experiment with one modification, we increase the initial concentration of the reactant in excess. That means initial concentration of reactant in experiment 2 bigger than that in experiment 1. What is the effect of this variation on the shape of the curve? Part A, on the shape of the curve of formation of product, concentration product equal Ft. First, the initial concentration of this reactant is a kinetic factor. When the initial concentration increases, the rate of formation of product increases. When the rate increases, that means at each instant, the concentration of product in experiment 2 should be bigger than the concentration of this product in experiment 1. But since the reaction is complete and the limiting reactant does not change, then the maximum limit, which is the concentration of product at end of the reaction, of the maximum limit of this curve does not change. Then the two curves have the same maximum limit, which is concentration of product at end of the reaction. Therefore, the curve concentration product equal GT, the new curve, is over the curve concentration product equal Ft. Graphically on the graph, this is the curve concentration product equal Ft. And this is the maximum limit, which is concentration of product at infinity. The new curve is above the first curve but below the maximum limit. This is the shape of the curve and the effect of the increase in concentration on the shape of curve of concentrated product equal Ft. Now, on the shape of the curve, concentration reactant equal Ft. Same justification, initial concentration is the kinetic factor. When initial concentration of reactant increases, the rate of disappearance of reactant increases. Now, the concentration of reactant at instant t, that means left, equal initial concentration of reactant minus concentration of reactant disappeared or reacted. When the rate of the reaction increases, that means the amount or the concentration of reacted disappeared or reacted increases. Therefore, the concentration of reactant left decreases. So that at each instant, the concentration of reactant left in experiment 2 is less than concentration of reactant left in experiment 1. Therefore, the curve concentration reactant equal GT, the new curve is below the curve concentration reactant equal Ft. Graphically, this is the curve concentration reactant equal Ft. The new curve is below the old one, concentration reactant equal GT. Effect of variation in concentration. Now the variation, if the variation is decrease in the concentration of a reactant, if we repeat the same experiment with one modification, we decrease the initial concentration of the reactant in excess. Initial concentration in experiment 2 less than that in experiment 1. What is the effect of this variation on the shape of the curve? First, on the shape of the curve, concentration product equal Ft. Same justification, initial concentration of reactant is kinetic factor. When the initial concentration decreases, the rate of formation of product decreases. That means at each instant, the concentration of product in experiment 2 is less than that in experiment 1, so that the new curve concentration product equal GT is below the curve concentration product equal Ft. On the graph, this is the curve concentration product equal Ft. This is the maximum limit. The new curve is below the old one. Now, on the shape of the curve concentration reactant equal Ft, same justification, initial concentration of reactant is the kinetic factor. When the initial concentration decreases, a rate of disappearance of reactant decreases. That means the concentration reacted decreases and concentration left increases, so that at each instant concentration of reactant left in experiment 2 is bigger than that in experiment 1, and the curve concentration reactant equal GT is over the curve concentration reactant equal Ft. On the graph, this is the curve concentration reactant equal Ft. The new one is above the old one. This is the shape effect of the variation in concentration on the shape of curve. Now application on this part. Consider the reaction of oxidation of 2-propanol, 5CCH8O plus 2MnO4 minus plus 6H plus give 5CCH6O plus 2Mn2 plus 8H2O. The obtained results are given in the following table. Variation of number of mole of the product CCH6O with time. 1. Plot the curve representing the variation of the number of moles of CCH6O as a function of time, and CCH6O equal Ft. In the interval of time 0, 20, we should start the curve from the point 0, the 0. At t equals 0, the number of mole of product equals 0. We take the following scale in abscissa 1 cm for 2 minutes, in ordinate 1 cm for 1 millimole. Part 2, the experiment realized above is repeated but with one modification. The reactants are added to a beaker containing 100 milliliters of distilled water. Trace on the same graph of question 1 the shape of the curve representing the variation of the number of moles of C3H6O as function of time, and C3H6O equals GT in the interval of time 0 to 1 minute. Justify. Part 1 is the curve. This is the curve, and C3H6O equal Ft. 2. In the presence of 100 milliliters of distilled water, the total volume of the reacting mixture increases so that the initial concentrations of reactants, all reactants, decrease. And since the initial concentration of reactants is a kinetic factor, so that the rate of the formation of C3H6O decreases because the initial concentration of reactants, the initial concentration of reactants decreases. Then, at each instant, number of mole of product formed in second experiment is less than number of mole of product formed in the first experiment. Therefore, the curve NC3H6O equal GT must be below the curve NC3H6O equal FT on the graph. The blue one is the old number of moles C3H6O equal Ft. The red one is the new curve NC3H6O equal GT below the curve representing the first experiment. This is the end of part 1, effect of variation of concentration on the rate of the reaction.